So welcome to our team. Our project's about a retractable syringe. Our team members are Jason, Susan, Gabby, and myself. So in the medical field, the occurrence of accidental needle pricks and needle contamination are a huge concern for the safety of patients and healthcare workers. Pretty much the most standard needles pose a risk for accidental needle prick injury, and it's estimated that over 600,000 healthcare workers incur a needle stick injury each year in the United States, and this leads to up to $1 billion in unnecessary costs. But a solution to this is a retractable needle. So pretty much upon full depression of the plunger, spring technology allows it to have rapid withdrawal back into the barrel of the device itself. So this is very marketable to hospitals and clinical settings where patient worker safety is incredibly important. And overall, the global market value was at 1.7 billion in 2018. So there's huge incentive for this technology.
So the retractable safety syringe is classified as Class 2 medical device, which means that it needs a 510(k) clearance by the FDA before being sold. This is a Class 2 medical device because a similar technology, just the regular old syringe, is already classified and approved as Class 2. So because of this, clearance can be achieved in a short time, about months, and it will be relatively inexpensive. Syringes in general must be compliant with ISO 7886 or ISO 7864 standards, like with other single-use syringes. Certain risks that we expect to happen with syringes are that the pressure in the syringe during plunger depression may cause the barrel to break, and so we will test this risk by conducting an internal pressure test on the syringe barrel. And another one would be that the user might poke themselves prior to using the syringe and then therefore activating the retraction mechanism and then rendering the syringe useless. So to mitigate this, we will design a cap for the needle. And in the case that the syringe can be crushed or contaminated without casing, we also design a case that will protect the syringe during transport.
So our overall system environment is that the syringe will be used in primarily room temperature hospital settings and vaccination sites, and we estimate that the widest temperature range would be minus 20 C to 40 C at the most. And important interfaces, well, the needle comes into contact with the body either intramuscularly or intravenously, so it has to be non-immunogenic. And the inner chamber that holds fluid must be inert so that it doesn't leach any chemicals into the solution. And the device is handheld, so it must be lightweight and have an easy grip.
To the left of the slide is a general diagram of how a syringe, like the vantage point retractable syringe, can be used. It's pretty simple. You just load it and then inject it into the patient, and upon depression of the plunger, the needle will retract into the body of the syringe to be disposed of. The main dimensions of the syringe will be 150 millimeters by 25 millimeters by 10 millimeters when the syringe is fully extended.
So we have a continuation of what our preliminary thoughts on what the mechanism of the spring could be. So this was sort of what we ended up with as our final design, where we had this plastic component coupled within the plunger components, so that once we depress the plunger almost completely, it will get caught here and essentially break this mechanism right here in the dark blue color. It'll break that piece, allowing the spring to expand and exert its, spring force that it has built up when it is assembled. All right, so here are our 4 requirements or verifications that we'll be conducting in our project. The first one is that the syringe case shall withstand a force of 900 newtons on all sides with a deformation of less than 1.1 millimeters to ensure that the case survives processing, transport, and accidents, of course. And that will be a static study with force applied to surfaces on the case. The second requirement is that the syringe barrel shall remain operable after internal pressures of 7.5 times 10 to the 5th power pascals or 109 psi by not deforming more than 0.1 millimeters on the inside to ensure that bulging does not occur. If bulging does occur, that will cause fluid to leak out and possibly backwards, and thus it would be a good device. And that will be a static study as well, with pressure applied on the inside of the barrel. The third requirement is that the spring and the retraction mechanism shall output forces greater than 4 newtons, so it can be able to pull the needle out of the skin when activated. And that will be done with a motion study / analysis coupled with a beautiful animation. The fourth requirement is that the syringe shall produce an exit velocity out of the needle such that the liquid will leave the needle in less than 0.1 of a second. And that will be done with flow express.
So for our manufacturing plan, we're primarily using polypropylene copolymer for our syringe body, our needle cap, and the syringe case because polypropylene copolymer has a number of ideal qualities. It's translucent, it's inert, has resistance to bacterial contamination, and also it provides a very ease of manufacturing, and it's cheap, it's lightweight, and has an ideal impact strength and toughness. For a needle, we would use stainless steel A316 or stainless steel 304. And for the needle itself, we would have nickel plating because we want corrosion resistance and biocompatibility. And then for the spring, we want also corrosion resistance, and it has an ideal yield strength of 205 megapascals. For the plunger stick and the plunger and the trigger, we would use polyether ketone PEEK because it's inert, it's autoclavable, and there's easy fabrication. It's lightweight, has good tensile strength and stuff like that. And for our plunger seal, we would use silicone rubber as it has the ideal frictional resistance to maintain a tight seal within the syringe barrel. And our primary fabrication process is injection molding, just because it's easy, it's fast, cheap. And for the needle, we would use tube drawing, electroplating, and for the spring, we would use CNC spring coiling.
All right, so here's a beautiful image of our full assembly design tree. So our basic features and advanced features are extruded boss and base, revolved boss, fillet, fillet, and the one shell, extruded cut, chamfer, and then we have the advanced features, the helical curve, lock to sweep, and sweep feature. So for the syringe body, here is a picture of the part in SolidWorks, and here is a drawing of it. So the features used here is locked, extruded base, and extruded cut. And for part 2 is a syringe needle. That's actually where we use a lot, or if not most, of our advanced features. We use extruded boss, sweep feature, but a thin locked, revolved boss / base. Here is our more detailed drawing of the syringe needle. As you can see, it is very dimensioned, and there is a spring specifications note on the side. Some other components that also use up some features. So this one used an extruded base / boss. Same with the drawings and the picture of the component inside of SolidWorks. Okay, same thing again. Plunger seal also used a revolved base boss / base drawing and then picture. The syringe trigger features used again revolved base picture in SolidWorks and picture of the drawing itself. And note here how there is like a center piece in the middle. That's a piece that will be broken for the spring mechanism to expand and pop the needle out. Part 6, the needle cap. We again use revolved boss / base. It's just such a great tool. And then fillet for some of the edges to make it look nicer and easier to handle and make.
So this is one of our first 2 parts, part 7 for our syringe case. This is made out of polypropylene copolymer and basically uses general features such as extruded cut and extruded boss base, in which we have several sections that are adjusted to wrap around the syringe itself with a gap of at least like 0.5 millimeters as to not immediately break the syringe upon the deformation of the case itself. And similar to the first half, the second half, the top portion of the syringe case is made in a similar way, but the rib features are not to just hold the syringe in place, but also to help stabilize the structure of the syringe case itself. So here we have a nice video of how the syringe components were put together in assembly.
So here's our assembly drawing. Again, we gave some general dimensions regarding the layout of each component such that it will fit into the casing. So for example, like the plunger will be like 60 millimeters from the wingtip, and the mass is 4.8 grams. For the interference detection and syringe volume, I just opened the interference detection feature in SolidWorks, and as you can see, there are no interferences, which is very good because that means it's well assembled. And for the volume, so this was like the inside volume of the syringe itself. So essentially, this is the volume of what's inside the barrel. It is a lot more than 1,000 cubic millimeters, and that's our syringe volume.
So in creating our full assembly of the case and syringe, the case was first put together by mates of concentric mate and a distance offset of 0.1 millimeters at the joints between the two, which will allow it to open and close. And then when inserting the syringe into the assembly itself, a concentric mate was made between the grooves that are made to outline the syringe itself, and then a parallel component between the point where the edge of where the syringe will be hole was the edge of the case itself. The mass property of the full assembly itself was about 64.78 grams, where the case made up the majority of about 60 grams, and the syringe 4.8, as mentioned before.
So the first problem that we looked at was making sure that our syringe case can actually maintain structural integrity to protect the syringe during shipping or being stepped on and other situations so that it doesn't damage the syringe with itself inside the case. So to do this, we did a linear static stress analysis with force applied. Simplifications where we assumed that the case was securely closed, so we made it closed, and that it experiences only compressive stress. and forces and fixtures were applied to opposing flat surfaces only. The elements used were default tetrahedral meshing option, which discretizes the assembly into tetrahedral shaped solid 3D elements. The loads applied were 900 newtons on the top, bottom, front, and back, and then the sides of the case. And then for the materials, we assume that the material is polypropylene copolymer as specified earlier, and our constraint was that opposite to the force where the load is applied is fixed. So our model check, pretty much I looked at the potential displacement of a solid block of polypropylene copolymer and see what that would be as a kind of rough comparison. It's not the most accurate, but it's kind of what we could do with this kind of situation. We were just looking at displacement. So for our results, what we found was we actually had positive margins of safety for the top, bottom, front, and back of the case. And we had negative margins of safety for the left and right sides of the case, but what we figured is that as long as the case is stored appropriately, which would be flat on like the top or the bottom, it would sufficiently protect the syringe. And our maximum displacement did exceed our requirement of just 0.1 millimeters, but it was an improvement compared to our initial simulations. And generally, it would be sufficient to protect the syringe in most daily situations. This is just some sample images of how our static force analysis looked like from the front and back. And then the same can be seen in the next two slides, where it's just from the top and bottom, and then from the left and the right sides.
So for second analysis, we did a syringe structural analysis, a stack test, where we were basically trying to see the structural integrity of the syringe itself, for which it would not break when the fluid is compressed and expelled from it. And so through hand calculations, we determined a pressure of 109 psi that we would apply to it, and we wanted to make sure that it does not deform more than 1 times 10 to the negative 2 millimeters after this pressure is applied. For the elements used, we use a default tetrahedral meshing, and as mentioned before, the load applied will be 109 psi to the inner surface. So the materials of connections constraints at the ends there are fixed, and the material is a polypropylene copolymer. But getting our results, we saw that there was a large deformation, but that was more than our requirement, but less than the deformation distance when the pressure was applied. Therefore, we failed our requirement. From this, we did learn that the greatest deformation was localized in the inner layer of the syringe, and that the center parts of the syringe exercise the least deformation. So this is just an image of our hand calculations that are used to determine the pressure that will be applied to the syringe for our analysis. Now, these are sample images of our syringe analysis, and these are displacements. So here we are seeing the inner part, and here we are seeing the general outer section of the syringe itself for displacement. Now, this slide and the next slide also shows generally what we saw first two slides, but instead of displacement, we are looking at stress itself. Okay, so for our margin of safety calculation for our pressure test, we used a safety factor of 2 and got a value of negative 0.56. And a negative value is undesirable, and we would preferably want a positive one, but this tells us that we might need to change the material or increase its thickness as we have overestimated the amount of pressure that the syringe can handle.
So for the third analysis, we studied the fluid dynamics through the syringe using Flow Express. The specific problem we're trying to address here is that the syringe should deposit its contents into the patient in a reasonable amount of time, just so that the needle inside the patient has limited contact to prevent further infection. The specific requirement that we want to achieve is that the syringe design shall produce an exit velocity out of the needle such that the liquid will leave the needle in less than the 10th of a second, which was calculated to be 0.48 meters per second. This value was calculated by measuring the length of the needle that the liquid will go through and then dividing that by a 10th of a second. When the plunger is fully depressed, any liquid left in the needle will safely exit in less than a 10th of a second. Like I said before, the analysis will be done using Flow Express, and any simplifications that we had is that the volume observed was from the bottom end of the stopper to about less than 2 millimeters from the edge of the slanted hole in the needle, because for Flow Express to work, it required perpendicular lids. In the simulation, the rubber stopper and trigger were not included so that mostly laminar flow would happen. Because it was Flow Express, no elements were used. The initial conditions used is that the initial velocity was 43.5 millimeters per second, and that's just the distance of the barrel from the wings to the part where it tapers off into the needle, which accounts for a flow rate of 1,229.93 millimeters cubed per second. Fluid was kept at a constant 25 degrees Celsius, and the output pressure was kept as atmospheric pressure. Again, the syringe body material was polypropylene copolymer, and the material of the needle is nickel-plated stainless steel 316 or 304. To do some preliminary studies of how the velocity of the syringe needle would be, the conservation of mass was used to calculate the exit velocity. An important assumption made is that in the cross-sectional area of both the barrel and the needle, velocity profile was assumed to be constant, so there is no variation in height with how the velocity would be. The found velocity is 2.446 meters per second, which was found to be greater than the goal velocity of 0.458 meters per second. After doing the flow express simulation, it is shown that velocities through the needle ranged from 1.893 to 3.786 meters per second, as shown with the green and yellow colors seen inside the needle. Since all of the velocities inside the needle are 1.893 meters per second or higher, we can safely assume that the velocities produced by the design will fulfill the requirement we previously have said. And the found velocity from the hand calculations fits in within this range. Yeah.
All right. Analysis 4, last and final analysis. Save the best for last. Come on. Is a motion study / analysis. So what is the problem? We weren't sure if the forces of the spring, when fully compressed, after it's been fully compressed, when it expands, whether or not that force is enough to pull the needle out of the arm. So our requirement was that it must exert at least 10 newtons upon triggering the syringe mechanism. It is designed such that when the mechanism is triggered, the syringe is fully compressed. And the motion analysis type is SolidWorks motion add-in. It's the linear motion analysis option, not the basic motion analysis option. Very, very important distinction here. For simplifications, as it says, some explanations will be provided later on in the presentation. But the crucial simplification made was that the spring used in the final simulation was not actually a real component / part, but instead it's simulated using the spring feature that's in the SolidWorks motion study. As you will see later on, even though it does not look like an actual compression spring, it has all the features of a compression spring. So in terms of connections, essentially only mates were used to fix the bottom plates, as you see later on, to fix the bottom, and then basically give the spring a concentric mate relationship. And that's basically it. Only one translational degree of freedom, essentially. Rotation was locked as well, so that's why. In terms of loads and drivers, there were no loads directly on the spring, but there was a motor that's set to move downwards 2.75 millimeters over 2 seconds. And that's the amount that the syringe mechanism will depress the spring before the mechanism triggers and the spring allowed to expand. So it's designed such that 2.75 millimeters would be enough to fully compress the spring, essentially. The results of the motion study was that the maximum force was 14 newtons. And that was nearly identical to the hand calculated value, which we will show you next. This result exceeded the requirement limitation of 4 newtons. There was a typo in the previous slide, but it's supposed to be 4 newtons, not 10 newtons. Lessons learned. So after making calculations, we realized that there are many ways to change the feature / performance of the spring. For example, we can change the core diameter to increase the spring force. So there's a lot of things we can explore possibly later on if we get there. Okay, so for the model check, as you can see, there was calculation of the K value for the spring. And basically, after doing some math and some explanation, it's not as complicated math as the previous one, but we ended up with 14.06 newtons, which is essentially what the simulation provided. And it makes sense because the spring it has all the same specifications as the one calculated here. All right, so for the first attempt, I tried to use actual spring component created by a helical coil feature and the sweep feature. So I did it both ways, and you can play a video if you would like, but it made a very cool animation, but it did not give the correct force readings. It does look nice though, so take a look. All right, so as you can see here, that red thing in the middle, it looks like a sausage, but it's not. It's actually a compression spring. It's just how it looks like, no matter how you change the specifications. I use the built-in spring feature. If you watch the video, I go through all the different specifications I set the spring to. It should match the ones that are done in the hand calculations. So here, we calculate the margin of safety using a factor of safety of 2. You see that 14 newtons, which was the force found from simulation and hand calculations, over 2 times our minimum requirement. That's 4 newtons, and the result was 0.75. And again, here positive margin of safety is desirable. And here is outline of what each member did. These are our sources, and I think that's it for us. The end. Okay, and there's an exercise after this. It won't be included in the video, but it'll include some revisions. And among other slides that we think might help with grading. Thank you for listening.
Great
It's
job, team.
12:05 a.m. Keep this in the recording. It's 12:05 a.m. in the morning. Please go easy on us. We all need sleep.
Yeah.